Welcome back. In this video, I'm going to introduce you to algorithms, these step-by-step instructions that we can build and use to solve problems. And if you've been following along so far, you may have seen this model, where we have these inputs and outputs, and we learned in the previous videos how a computer can represent these inputs and outputs using systems like binary, ASCII, Unicode, RGB, and so on. But now we're going to focus on the black box itself, and mainly on algorithms. We'll see exactly what an algorithm is, how we can design these algorithms based on real-world solutions, and how we can measure how efficient our algorithms are. Now, algorithms are something that we're going to be going over more once we get some more coding under our belt, but this video is meant to be an introduction. If something doesn't quite make sense, make sure and post your questions in the comments section. Remember, there are no dumb questions. Now, this image, yes, it's a model with which we can use to help solve problems and understand what's going on, but really, this is an example of an abstraction. And this is a term you'll hear a lot in the field of computer science, and all it really means is the simplification of something, so that we don't have to focus on these low-level binary implementation details and rather just focus on the higher goals at hand that we're trying to solve. Now, a good example of this is a car. You don't have to understand exactly how the engine and the suspension works to drive the car. You just have to know how to start it, put it in gear, and turn, etc. So you don't have to understand every single part of the car just to drive it. And with abstraction, we can hide some of these lower level implementations. So with that said, let's focus on this black box. And what does this box represent? Well, it represents an algorithm, some step-by-step instructions for solving a problem. And let's look at an example of this and how we might use an algorithm to solve a problem. Let's say that we have a dictionary, and the goal at hand is to find a specific word. In this example, we're going to say that the dictionary has 1,000 pages, and the word we want to find in the dictionary is the word computer. So what steps could we take to find this word that we're looking for? And I'll propose that we could start on page 1 and look at each word, and if we don't find the word computer, then we go to page 2 and do the same thing. And then page 3 and 4 and 5, all the way until we're either at the end of the dictionary or we find the word that we're looking for. And I'll ask the question, is this algorithm correct? If I use this approach and the word computer is in the dictionary, will this algorithm find the word? And the answer is yes. It'll be very slow and tedious, but if the word is there, we'll eventually find it. But maybe we can do better. What about if we went 2 pages at a time? So 2, 4, 6, 8, 10, etc. And it would seem that with this we could go twice as fast. But is this algorithm correct? Well, no, it's not. And why? Because we're skipping every other page. And just maybe we get unlucky and the word computer is on one of the pages we skipped. But we could fix this. Maybe we just check if we get to the D section, for example, that we double back a page. So it would seem that this algorithm of 2 pages at a time, and granted we would have to take that extra step of doubling back, but it would be reasonable to say that this algorithm is twice as fast. But what do we do as humans when we're looking for a word in a dictionary? Well, we know that the dictionary is in alphabetical order, and we'll usually open to roughly half the book, and we'll see that we're in the end section, for example. And so now what do we know about where the word computer is? Well, we passed it because we know it's in the C section, and C comes before N. And we can essentially throw half of this problem away. We know that the word computer isn't in the right half of the dictionary, and then we can pretty much repeat this algorithm. We can open to roughly half of just the left half of the book, and perhaps now we're in the F section. So now what do we know? Well, we're getting closer, but we're still past the word we're looking for. So we can essentially throw the back half of the problem away because we know the computer isn't in the section past F, and we know it has to be before that. So now if we started with 1,000 pages, after looking at just one page, we threw half of this problem away. So we're down to about 500 pages. And we repeat this. And we're down to 250 pages, and then 125, and then about 61, and 32, 16, 8, 4, 2. And finally, we're left with one page, which either contains the word computer, or it doesn't. And we can conclude that the word computer isn't in this dictionary. And what does this say about the performance of this algorithm? Well, that first algorithm where we went page by page would have taken us 1,000 steps if we had a 1,000-page dictionary. And that second algorithm, where we went 2 pages at a time, would have been roughly twice as fast, or taken us about 500 steps. And really 501 because we would have had to double back in case we passed the word we were looking for. But again, a correct algorithm. But this final algorithm, where we kept splitting the problem in half and in half, would seem to be a fundamentally different algorithm. If we started with 1,000 pages, then after one step, we would be down to 500. Another step, we would be down to 250, and so on and so on. In this algorithm, it would only take us like 8 or 9 steps to find the correct word that we're looking for. And if we added another 1,000 pages and we had a 2,000-page dictionary, what could we consider? Well, that first algorithm is now going to take us 2,000 steps, and the second would take us about 1,000 steps. But what about the third? Well, it would only take one more step, because the first step would be to cut it down from 2,000 pages to 1,000 pages. And we're right back where we had the 1,000-page example. So it would take about 10 steps in total. And when we consider this running time for algorithms, we can start to see and compare the efficiency of an algorithm. And we can actually chart these too. So let's say we had this chart, and the x-axis is the size of the problem, and the y-axis is the time it's going to take to solve the problem. Well, we can chart that first algorithm with a straight line. And why? Because it's a linear algorithm. The more pages that we add, the longer it's going to take. And if we added twice as many pages, it's going to take twice as long, or twice the steps. And we tend to generalize these numbers of steps as n. Yes, technically, it's 1,000 steps, but the same would be true if we had any other number that we used for n. As an example, if we had a 500-page book, instead it's still going to scale in a linear fashion. So we can just say n steps. Similarly, that second algorithm, yes, it's twice as fast, but again, it's a linear algorithm, and we can represent it with a straight line too. Because this one is twice as fast, we can represent this one as n divided by 2. Because again, if n is 1,000 pages, and this algorithm will take 500 steps, or n divided by 2 steps. But this final algorithm has a fundamentally different shape. And I'm not sure how familiar you are with your logarithms, but they're just a fancy way of saying that this problem gets split in half every step of the way. And we can chart it like this. Log base 2 of n is the technical formula for representing cutting something in half over and over again. And yes, this line of the third algorithm, where we kept dividing and conquering, if you will, is going to keep increasing with larger problems, but at a much smaller rate than these first two algorithms. And this kind of divide and conquer algorithm is essentially what most computers are doing when they're searching for something, because it's so much faster than these other methods. And you can imagine these large companies with huge data sets like Google and Facebook, they would have to develop something more sophisticated like these algorithms, or they would be extremely slow. So, as an exercise, I want you to try to think of an algorithm for how you could sort a set of numbers. For example, if I gave you the numbers 5, 3, 7, 9, and 1 in this order, how could you methodically, step by step, go about returning the values 1, 3, 5, 7, 9 in this order, from smallest to largest? Post your answers in the comments section, and this is going to conclude the intro to algorithms. Thank you so much for watching. I hope you got some value out of this video, and in the next one we're going to introduce something called pseudocode and see how we can translate these ideas of algorithms into actual code.